Hi everyone, today we are going to start process synchronization. Process synchronization or concurrency. Process synchronization is fundamental for managing shared resources. In a multi-threaded and multi-process environment, it prevents data corruption. What we will learn in this chapter, this is about getting process to coordinate with each other, how to process work with resources that must be shared between them, how do we go about acquiring logs to protect regions of memory, and run condition. We are going to cover the topics critical section problem, synchronization hardware, and distributed system and the problem race condition and critical section. The race around condition, multi-process or thread access share data, and the final outcome depends unpredictably on the exact order of the execution. This can lead to inconsistent mistakes. Now, critical section, a specific segment of code where shared resources are accessed, only one threaded or process should be allowed to execute within the section at any given time to ensure data integrity. The hardware required to support critical section must have minimally indivisible instructions. What are these? Atomic load, store, test instruction. For instance, if a store and test occurs simultaneously, the test get either the old or the new, but not some combinations. Two atomic instructions if execution simultaneously behaves if executed sequentially. There are some solutions of it, hardware solutions for disabling the interprets. Mutex law, mutual exclusion. Mechanism number one is mutex locks, mutual exclusion. Mutex locks are the simplest and most common synchronized primitive. They ensure that one thread can either a critical section at any given time, thereby providing mutual exclusion for shared data. The mechanism involves two primary operations: lock to acquire the mutex before entering the critical section, and unlock to release it upon exiting. This ensures that a shared resource is protected during access. Mutex are widely implemented in concurrency libraries such as POSIX threads, pthreads, and Java's built-in concurrency utilities. The overhead of each lock and unlock operation is typically in the microseconds, making them efficient for frequent uses. Then there are mechanism number two, semaphores. So, what is semaphores? Semaphores is count. There are semaphores. Semaphores can be used to force synchronization precedence if the preceder does a signal at end and the follower does wait at the beginning. For example, here we want P1 to execute before P2. P1 statement signal, P2 waits in statement 2. We don't want to loop on PC, so we'll suspend instead. Block on semaphores is equal to false. Wake up on signal, semaphores becomes true. There may be numerous processes waiting for the semaphores, so keep a list of blocked processes. Wake up one of the blocked processes upon getting a signal. Choice of who depends on strategy. To prevent looping, we redefine the semaphore structure as type def struct, int struct process, semaphores, value list, linked list of PTBL waiting on as, process synchronization. Counting semaphores manages access to resources with a finite number of instances. The semaphore's value indicates the number of available resources, allowing multiple process up that limit. Binary semaphores. functions like a mutex, allowing only one process to access a critical section at a time. Its value is either 0 locked or 1 unlocked, providing mutual exclusion. A semaphore is an integer variable used to control access to a common resource by multiple processes. If it operates via two atomic operations with or P, which decrements the semaphore and blocks if negative, and signal or V, which increments it and wakes a waiting process. As discussed, the first proposed semaphores in 1965 as a solution to the producer-consumer problem. So this is our mechanism of semaphores. There are deadlock of it. Deadlocks may occur when two or more processes try to get the same multiple resources at the same time. Like P1, wait Q, signal as signal Q. How can be fixed? High railway now Andes, a practical problem. High in Andes mountains, there are two critical circular railway lines. Sorry. Monitors. Monitors are high-level synchronization constructs that encapsulate shared data and procedures, methods that operate on the data. They abstract away the complexity of mutexes and condition variables, providing a more structured approach to concurrency control. A key feature of monitors is that they guarantee mutual exclusions. Only one thread can be active within the monitor procedure at any given time. They also wait and signal or notify in Java. Operations for threaded coordination, allowing thread to wait for specific condition to met before proceeding. Languages like Java and C++ have built-in monitor support, simplifying the development of thread-safe code by handling much of underlying synchronization complexity automatically. Monitors. They two high-level synchronization concept that allows the safe sharing of an abstract data type among concurrent processes. To allow two processes to wait within the monitor, a condition variable must be declared as condition x, y. Condition variable can only be used with the operation wait and signal. The operation x dot wait means that the process invoking this operation is suspended until another process invokes x dot signal. The x dot signal operation resumes exactly one suspended process. If no process is suspended, then the signal operation has no effect. Monitors. Message passing. Mechanism number 4, message passing. Send and receiver model. Process communicate by sending and receiving messages. This inherently synchronizes them as a sender might block until the message is received, or the receiver might block until a message arrives. Decoupled system. Ideal for distributed environments where processes don't share memory, it promotes modularity and resilience, as failures in one process are less likely to affect other directly. Scalability facilitates scaling by allowing new processes to be added without requiring extensive re-architecting or shared memory structure. Examples include MPI and Erlang's actor model. Now, all the mechanisms are over and common pitfalls. The common pitfalls are like deadlock, live lock, starvation. So first we will understand what is deadlock. Deadlock occurs when two or more processes are indefinitely waiting for resources held by each other, leading to standstill. It requires four Kaufman conditions: mutual exclusion, hold, and wait. No preemption and circular wait. Live lock. Processes repeatedly changes their state in response to each other's action, but no actual progress is made. This is akin to two people trying to pass each other in a hallway, constantly stepping aside into each other's path. We can understand deadlock by also another example like a pen and a page. You can't write without a pen, and without a page, where you will write with that pen? So they are need each other. But if they don't meet each other's requirement, the processes, then it will not. Starvation. A starvation where a process is indefinitely denied access to shared resources, even though the resources become available. This can happen if a scheduling algorithm constantly prioritizes other processes. This is the performance and scalability consideration graph. With this, we can, the upper one is for the performance consideration and scalability. Real world application and best practices. Operating system essential for controlling access to kernel data structure and efficiency scheduling process. Databases can also be crucial for ensuring transaction management, ACID properties, and managing concurrent read and write operation without data corruption. Cloud computing can also. Conclusion. Mastering concurrency. Process synchronization is not merely a technical detail. It is a critical component for building reliable and efficient concurrent systems. The optimal choice of synchronization mechanism is sorry for the disturbance. Conclusion. Mastering concurrency. Process synchronization is not merely a technical detail, it is a critical component for building reliable and efficient concurrent system. The optimal choice of synchronization mechanism is highly dependent on the specific system architecture and its unique requirement. A deep understanding of common pitfalls such as deadlock, live lock, and starvation is absolutely vital for designing robust and resilient software. Ultimately, continuous vigilance through testing and careful design remain key to successfully managing the interior interaction of concurrent processes. Now, I would like to conclude these slides. Thank you for listening me. Thank you for listening me. Listening me. Thank you and bye bye. Bye.